Hey guys, and welcome back to Data Science, Deep Learning in Python Part 1. In this lecture, we're going to cover the problem, what happens if your output is more than two categories? So previously, we only discussed binary classification, for which there are many real-world applications. For example, we could take as inputs the humidity, whether or not the ground is wet, the month, the geographical coordinates, and try to predict whether or not it will rain. Another example is we could take inputs like how frequently someone exercises, their age, their BMI, and what types of food they eat, and try to predict whether or not they will get a certain disease. So these are typically yes or no questions. But in many cases, there are more than just two classes to choose from. Suppose you're Facebook and you'd like to tag all of the photos that get uploaded to your database. So far, Facebook is able to tag faces, but we could tag other things as well. Cars, wedding dresses, what environment the photo is in, like a bar or outside in nature. This would be very valuable data for Facebook because they use the things on your profile to determine what advertisements to show you. There is also the famous MNIST dataset, where you have to try and categorize each image as a digit between 0 and 9. So let's talk about how we can extend the logistic unit to handle more than two classes. Recall that when we have two classes, we only need one output. This is because it can represent the probability of one class, and then the other class can be represented by 1 minus that probability. But we can also do this another way. We could have two output nodes, and we could just normalize them so that they sum to 1. In fact, this is exactly what we'll do. We'll also exponentiate them first to make sure that they are both positive. So this is how you would calculate the output of class 1. And this is how you would calculate the output of class 2. Notice that the weights are now no longer a vector as they were in logistic regression. Since every input node has to be connected to every output node, you have d input nodes and 2 output nodes, so the total number of weights is 2 times d. And the weights are stored in a matrix of size d by 2. Notice that this is very easy to extend to k classes. We have a new weight matrix of dimension d by k, and we calculate the outputs by first exponentiating every output and then normalizing it. The output, which I've called A, is usually called the activation. Hey guys, and welcome back to this class, Deep Learning in Python Part 1. In this lecture, we are going to discuss when are the Sigmoid and Softmax equivalent. We're going to work through a little bit of the math to show you the equivalence of the Sigmoid and Softmax. First, let's write out the equation for Softmax. We know that the probability that y equals 1 given x is the exponential of w1 transpose x divided by the exponential of w1 transpose x plus the exponential of w0 transpose x. The probability of y equals 0 given x is just 1 minus that. So let's divide the first equation by exponential of w1 transpose x on the top and the bottom. Try this yourself and see what you get. I want you guys to pause this video and see if you can find the answer yourself before I go to the next slide. Now this is in the same form as the sigmoid, so what does this mean? It means that having two weights is actually redundant when there are only two classes. From a software design perspective, it's safer to just always use Softmax, since it can handle not only the sigmoid case where k equals 2, but any value of k.